Hello guys, welcome back. In this video, let us understood different types of layers. Based on the task, let's classify the layers into different types. So first, for input, we have input layer. So let's classify based on task. So since that's also one of the type of layer, I mentioned that. For input, we have input layer. We mentioned that by using input shape. Then for feed forward networks. So if you see any transformers or any ML models, those contain definitely some feed forward networks. So those, how do we represent? For commonly used feed forward neural networks, we use this dense layer. So why do we use this dense layer? To represent feed forward network. Each neuron in this dense layer is connected to every neuron in the previous layer. Each neuron in this dense layer is connected to every neuron in the previous dense layer. It performs transformations like linear transformations. It can perform by using activation functions. And you have seen, you can use this dense layer for input, hidden states, as well as output as well. In this dense layer, you can provide input function to represent the input neurons or input layer neurons, and you can use this dense layer or feed forward network layer as a hidden layer or output layer by providing some activation function in it. This is the most commonly and highly used layer. So now let's see the another layer. Let's say I want to perform natural language processing or predicting the time series, or let's say I want to generate the next sentence. This require to remember the hidden state. That is, it require to maintain a hidden state captured information. That is based on the previous input, whatever the result generated for the previous input, that result we need to store it somewhere in the hidden states. For those types of tasks like natural language processing or sequence generation or predicting time series, we use RNN layers. Those are simple RNN layers. These acts like a short memory. These will remember the or maintain a hidden state that captures information from previous input, and it can able to process sequential data. So in real time, you might have requirement for long time memory for performing this natural language processing task. You might have requirement for long range dependencies as well, like language translation or speech recognition. For these tasks, we need to remember a long range dependencies. We need long range dependencies. So long range dependencies are crucial in these tasks like language translation or speech recognition. During this time, in order to provide long short term memory, we use LSTM layer. This is a simple RNN is one layer. This dense is one type of layer. This LSTM is also another type of layer. This is a gated layer. Actually, the data, it's a special type of recurrent layer only, where it can learn long-term dependencies using gates to control the flow of information. It uses the gates to learn long-term dependencies. So this is just for NLP based task with remembering long-term dependencies. Based on the requirement, we are expecting faster training of our models on large data sets. That is high performance based models we are expecting, similar to LSTMs, but with simplified architecture that uses a few gates, makes it faster to train while still capturing the dependencies. Like that type of architecture or layer we are expecting in future. That type of layer also developed, that is GRU, gated recurrent unit. What is that? Gated recurrent unit. It is same like LSTM, but it also provides you highest performance since it is designed with less number of fewer gates. So that's why this also built by using gates only, but less number of gates compared to this, so performance is high here. Then we also have one more layer. We also have layers regarding improve generalization. While generating, to improve the generalization, other than depending on specific neurons, we'll use one more layer, that is dropout layer. By using this dropout layer, we can able to reduce the reliance on specific neurons or dependence on specific neurons and improve the generalized output. So for such type of tasks, we use this dropout layer. Don't worry, after explaining theory, I'll show you practical implementation as well. And then we might have requirement like deep networks. We might have use cases like deep networks to improve training speed and model performance. For such type of tasks, we need batch normalization layer. So that layer is also there. That is batch normalization layer for deep networks. For improving the training speed and model performance, we use this batch normalization layer. So not only these are related to, you can observe these all are related to text, right? Yes. We also have some models. We also have some models related to vision, computer vision based. By using the computer vision, if you want to perform tasks like image recognition, object detection, and other tasks, then for such type of tasks also we have some layer, that is convolutional layer. What is that? Convolutional layer. We use the convolutional layer CONV2 2D. We can able to do this computer vision based task. After performing computer vision based task, we may get high features mapped data. Then in order to reduce or downsample the feature maps and retain the important features, we have one more layer, that is a polling layer. What is that? Polling layer. This is not convolution, it's a convolutional layer. Now we will see, so these are the different types of layers based on their tasks. Now let us see how to implement these as well. Now since we are seeing multiple layers, let's define a model. So I'm just commenting these all. What are the model that I have defined previously, that I'm commenting. And here I want to define a model. So this is also same from TensorFlow.keras. You need to import the models as well as the layers. Basically, previously at the starting days, this Keras is a independent API. After some days, this is integrated with this TensorFlow library. Then we are having the interacted Keras library right now that is available with this TensorFlow. That's what we are using right now. Now let's see the different types of layers. In different types of layers, so I have explained to you, we can able to define the input layer by using the input shape. So let's define some random model by using models dot sequential. By using models dot sequential and defining a function. So this is our model that we define. Currently in this model, there are no layers are there. Now I want to add a layer to it. So model dot add. This function you can use to add layers. So by using the layers that you imported, I'm just adding a layer. Since this is the first layer or input layer, we need to specify that as input layer. And we need to provide the shape. Like what is the shape? The input shape that I'm providing here. That input shape is nothing but what are the input dimension that you have. Input dimension. And this we need to provide as a format of tuple. This input dimension currently let's say I have a training data set. So for the training data set, if I want the dimension for it, currently it is loaded in a pandas data set. So that's why currently for that training data set, I want the shape. This is the trained data set in a pandas. Currently it's present. To get the shape, I'm providing a shape of first value. So that's why I'm providing 1. In this way, by using the input layer, you can able to define your input layers. So then after, let's also see how to define other layers like dense layer. So why do we use the dense layer? We use the dense layer in order to represent the feed forward network. In order to represent the feed forward network, we use the dense layers. Let's also see how to define the dense layer. Dense of, we need to provide the number of neurons. I'm providing a 64, and we need to provide the activation function for this dense layer. Even though it's an optional, or you can provide it as you wish. Currently, I want to use this layer for hidden layer. Input layer I provided. I want to use this for hidden layer, so I'm providing a ReLU. I want to use this activation function for this hidden layer, rectified linear unit. I want to use it, so that's why I'm providing it. You can also define this input layer in another way as well. That is a model. I'm just commenting the previous one. By using the dense layer also, you can able to define this input layer. That is a layers dot dense of. So how many neurons you want to provide? Let's say I want to provide 64. And you need to provide the input shape. To tell this is regarding the input layer, you need to provide the input shape. And here you need to provide the dimension, input dimension you need to provide, and in the form of tuple you need to provide. So this is one way to define your input layer, and this is another way to define your input layer. And hidden layers you can able to define by using this dense layer itself. You can do that as well. Then, so this is about a dense layer, how to define it. That is for feed forward networks, we use this dense layer to define it. And in this activation function, we'll provide what are the activation function that we want to use. Then let's also see the other, that is a small RNN model, how to define a small RNN layer. Regarding a dense layer, it is dense layer we have seen. Let's also see how to use small RNN for, that is a small recursive neural network, for NLP based tasks. So in order to define that layer, so it's also the same. That is a model dot add of the layer. You can define it by using layers dot simple RNN, and you need to provide the units. That is, this units actually represents the total number of neurons designed to process the sequential data by maintaining a hidden state. That hidden state actually captures the information of previous inputs. By using the previous inputs, it can able to process and it can able to generate or predict the next upcoming sequence or natural language processing task also it can able to do by using this simple RNN. Since it's a short-term memory, if we require long-term memory with this small RNN plus long-term memory, long short-term memory, then we need to go for LSTMs. These are acts like a memory units for your neural networks. So these also you can able to create in a similar way. That is models.add of layers dot LSTM of units you need to specify, like how many units you are providing to remember that memory. Currently, I'm using 50 units. So again, these LSTMs are generated by using gates only. To provide in future, we are having a high requirement of high performance based training or faster training. In simply, you can say faster training. So in order to train our model fastly, we are having requirement to optimize these LSTMs as well. So after doing optimizing of these LSTMs to provide fast training by reducing the total number of gates actually present in the architecture, by simplifying the architecture of LSTM, they generated GRU, that is a gated recurrent unit. So by using this, we can able to provide LSTM with faster training on larger data sets. So how to define it? How to add it to our model? To add it to our model, it's also the same layers.gru of how much units you want to specify for it. 50 units. So that's why I'm specifying like this. So these all are related to NLP based tasks. And this is related to feed forward network, that is a dense layer. And if you consider these two are the input layers. And at last, after these, we have also introduced, they're also introduced for computer vision based tasks. So what are computer vision based tasks? Like image recognition, image related tasks, or object recognition tasks, or image recognition tasks, and so on. Other tasks also, we can use this computer vision based layer. So how we define that layer? So same, let's see how to add that layer to our model. In order to add that layer, so simple layers dot conv 2D. You can use this conv 2D to use that layer. And here also three components we need to know. That is filters. Don't worry, I'll explain you this. And kernel size. This kernel size is nothing but your filter size. And activation layer. If you want to include any activation layer, activation function, then that also you need to include here. So I'll explain you what happens if I provide this layer. This layer, actually, how we see an image. An image will identify based on its an image will identify based on its intensity, right? Yes. So based on the brightness of the image, we'll identify that's related to red color or blue color, like that. In background, if you go in deep, then how this intensity is represented? This intensity is represented in the form of numerical vectors. In the form of numerical vectors, or you can say in technically matrices or grid format will represent this data. How we represent this data? We represent this data in the form of a grid or a matrix. Let's take a sample matrix or how it look like. Let's say this is my sample matrix with 3 rows, and it also have 3 columns, like -1, -1, -1 in the first column, and 0, 0, 0, 0 in the second column, second row, and in the third row I have 1, 1, 1. So like this I have my data. So actually like this your data will be represented background. Either it may be an image or anything. Then we see this data in the form of intensity. We are computing this whole data by using any one of the software, and we are seeing that data in the form of intensity of light, either in RGB or gray color. Based on that, we are identifying different colors. Based on those different colors of each and every pixel, we are seeing the whole image with multiple pixels and we are able to see the output image. Let's say if we want to perform any filtering, then how that filtering will be happened. In order to apply filtering to any image, let's say this is my matrix image I want to apply some filtering to this by using some 2D matrix. That is, I want to apply some filtering by using some 2D matrix. That 2D matrix will be 1, 1 and yes, 1, 1. Then how can I able to apply that filtering to this matrix? So first, this data will be taken and this 2 rows and 2 columns. We'll first consider these 2 rows and these two rows as well as this first column, and it will do this mask will cover this data, this 4 values, and it can able to perform its computation. Like it can perform the multiplication, it can perform the matrix multiplication, and whatever the results that it will add and find the result, and based on that result, whatever it will get, it will represent that summation of those product information here in this middle pixel as a value of that whole data after applying filtering. So in the similar way, after considering these 4, just our kernel will move a bit right. It will consider next 4, like these 2 and these 2 and these 2 and these 2, like these 4 it will consider, and again the matrix multiplication product will be happened, and it will do the summation and it will find the next pixel, that is this. So after identifying this, it won't go next because there is no data. It will go again down and it will consider this data as well as this data. These 4 values it will consider, and again considering the it will consider the product of 2 matrices and find the result and store the result in this pixel. In the similar way, again it will take these 4 values and multiplied with this, and it will get the result and store the result here. So like this, it will get these 2 values as well as these 2 values, and after filtering, the output will be only these 4 values. After filtering with this data, with this grid to our actual image, we get a bit featured. That is, we get a featured image with these 4 rows only, whereas the outer edge will be neglected. Here, this will become neglected. This will become removed, and we'll get the data at these 4 points based on our applied filter. That is this. By using those data of intensities, we can able to identify few concepts, like we can able to detect the edge of an image, right? Yes, the intensity is very high at edge, because if you see here, it will be blue. Like if you consider an image, the edges are dark, whereas the other points are not dark. You can see this line is dark. After this, if you consider, the intensity is highly different to this white line as well as this other line, this black also, this white also. You can see the intensity is highly different. So based on that difference, we can able to predict, we can able to identify that edges, and we can able to identify the objects as well by identifying such edges, by training our neural networks with such models, with such data, with such features. We can able to predict specific objects or images and recognize some images based on those edges after applying this filtering. This is the basic method of filtering this matrix with this data, with this matrix of grid. Actually, our image data will be a high dimensional grid, high dimensional 2D grid only. We provide some kernel size. Based on that kernel size, like this, one more grid will be created, and based on our grid, whatever the image that we are providing, that image will be filtered, and we'll get identify the specific features based on the filter that we provide. If we provide this mask, then based on this, one feature will be identified. Like that, how many filters that we specify, those many different types of masks are passed to our image or object that we provided. And then based on those many filters, it will identify, this convolutional 2D layer will identify or predict the actual features of the image. And then based on those features, it will load to the model. It will load those all weights to the model. Here, this kernel size represent what is the filter size that we are expecting to apply on our given input image. And what is these filters? These filters indicates the different types of how many filters that we are applying on each sample data. Let's say we are passing 4 batch data into this model. Whatever the model that we have, to this model, we are passing 4 chunks of data. Then 4 times, each and every time, how many times the model will be updated is, if we pass 4 batch, let's consider the data in the form of a batch. 4 batches of image we are passing to this. We are passing to this model. Then what happens is this model will be actually updated exactly 4 into 32 number of times. 4 into 32 number of times. That is each batch. For each batch, whatever the image that you provide, for each image batch, 32 features will be identified. Since we are providing 4 batches, 4 into 32, that is 4 2 are 8, 4 3 are 12. So 128 updates or features or training data will be happened on our model. So this much amount of data will be stored or trained on our model based on the weights that are identified each and every time. Here, for each input, we are applying 32 filters. So that's why if we are providing an image in the form of 4 batches or 4 parts, then so totally these many updates or processings will be happened, and this much amount of data will be stored. So that is in detail about this conv 2D layer filters as well as kernel size. Now, after generating the result, how the result will be? The result will be a high dimensioned, that is high layered. More number of features identified samples are there in our output image, right? Yes. So now I don't want that high ended data. Like I want to down sample. That is to down sample. I want to down sample whatever the data I have, feature maps I have, and retain. Even though I down sample the feature maps, I need to retain important features. So for this, we'll use polling. What is that? Polling. So how to implement that polling? How to add that layer? Model dot add layers dot max polling. Max polling 2D of. We need to provide the pole size. We need to provide the pole size. So previously it's a 3 by 3 grid. Now I am providing 2 by 2. So what does this 2 by 2 indicate is? So after this polling, let's say if you have a matrix of height h, or if you have an image of height h and the width w, then after polling, your output image will be less dimensioned image, that is h by 2 height and w by 2 width. Image you will get after polling, since you provided polling size as 2, 2. So that's what happened in the background. After polling, your data will be like this, like h and w be the dimensions of your image, then that will be converted to h by 2 and w by 2. So these are the layers, important layers that we need to consider while creating any layer. You have seen different input layers, how they will be, and the dense layer you have seen for feed forward network. For small RNN networks, like for classification, generation, prediction tasks, you have seen how to create this small RNN layer. And for long memory, you have seen these LSTMs, long short-term memory. With this long short-term memory, if you are expecting fast performance for training, then you have seen this GRU, gated recurrent unit. And for vision-based tasks, computer vision-based tasks, you have seen this convolution 2D. And after generating the outputs of this conv 2D, you have also seen the max polling 2D for doing a downsampling of your features that are mapped here. So one more parameter we need to pass, that is input shape, in order to specify what is the shape of our image. So these are the things, these are the different layers that we need to consider while creating our layers for neural network. I hope you understood this video and you understood the implementation of different layers for neural networks. So while creating your ML model with neural networks, then based on the task that you have, you need to define the layer, you need to add the layer to your model based on your requirement. So these are the general, mostly commonly used layers. You can choose based on your requirement. I hope you understood when do you use what layer and what is preferred compared to others. I think I need to explain this dropout layer as well as this batch normalization layer as well, implementation. So let's also see that and finish the session. Now I want to add that dropout layer. So in order to add the dropout layer to my model, so just use the layers dot dropout of. So what is the rate that you want to provide for dropout, that you need to specify. Currently I'm providing a 0.5. So based on the rate that you provide, it will improve the generalized content by reducing the dependency or reliance on specific neurons. So this is the dropout layer implementation. This is how the dropout layers you need to implement. Then we'll also see how to implement batch normalization layer. We use these layers actually for deep we often use it in deep networks to improve training speed and model performance. How do we add these layers to our model is layers dot batch normalization. So that's it. You can able to add batch normalization layers to your models like this in simple. So like this, you can able to implement these things while creating your ML based neural network models. So this is all about when to use what layer and how to use what layer. I hope you understood this video and you got some knowledge regarding when to use what layer and how to use what layer. I hope this video is useful. If you feel this video is useful, then please like, share, subscribe, and hit the bell icon to get the latest updates. Thanks for watching again. See you back in the next video with another interesting topic. Until then, bye.